All right, well, good morning, everybody. Thank you for joining Flex Train, a flexible training opportunity brought to you by Johnstone Supply. So as we continue talking about inverter technology and particularly, inverter diagnostics and troubleshooting, that's where we're at right now. Last week we talked about using the diagnostic tools that are going to be available for these new pieces of equipment, using error code retrieving that is in the thermostats, these intelligent communicating thermostats, using the individual components to be able to focus in on what those error codes are, to be able to see a little bit more detail than maybe what is only at the thermostat. Well, this week we want to talk about what happens when we need to start testing these pieces, right? Because we've changed a lot of our technology. We're not using the same types of switches that we were before. We're now using sensors and transducers that are using variable voltages. And it really comes back to understanding that whole communicating 5-volt DC technology, right? It's understanding that a lot of different manufacturers are using the same technology. They're using that 5-volt DC communicating platform that came from Emerson from 1990s climate talk. And we're still going to continue using some of those 5-volt DC technologies even to be able to run through the rest of our sensors, our inputs and our outputs sometimes. So we want to spend a little bit of time today talking about how those things intermingle. So Jesse and I have been working on this FIT tips program. So we sell Daikin here at the Johnstone Grimmy Group, and Daikin FIT is really becoming like the hot topic in the inverter industry in general, just because it's using that mini split style outdoor unit, but it's using that electronic expansion valve indoor coil so that we're reading that true superheat off from that indoor equipment instead of reading it at the outdoor equipment like most of the manufacturers are doing. So we built this FIT Tips program, which is basically it's an installation and service troubleshooting that pertains particularly to the Daikin FIT. But in using that understanding, we can also relay this same principle over into other manufacturers of equipment. So we're going to focus on Daikin FIT, but just understand that it really is the same style of communicating technology that we're using in inverters. So if we look at what we're doing electrically wise, we really have to understand how we're communicating. Because when we were talking about a 24-volt AC, a legacy style communication coming from a thermostat and talking to, not really talking, but making switches for our equipment, we were just sending out 24 volts AC, and it was it was making some kind of an action. It was turning on some type of a switch, contactor, whatever it was. So we were applying a load on those two wires, right? If we just had 24 volts going to a contactor, we had common on one side of a contactor, and we had our 24 volts AC that was feeding the other side. And it didn't really matter which way the current flowed. We were just energizing some type of a winding, right? Well, everything changed when we went to communicating DC signals, because we're now going to start relying on ground as a reference point. I'll draw that out here in a minute just to help that look a little bit clearer as to how that DC signal is actually functioning. But the thing that we really need to understand is that it is all pertaining to a reference to ground. And ground is going to be an extremely important component with our new communicating network, right? We're only using two wires, but we're sending a lot of signal on those two wires. We actually have a bandwidth in there. It's just like any other telecommunications network or cable. We're using that bandwidth between those two wires in reference to ground. And that's where our communication is going to happen. So, a lot of these components have additional power supplies that need to be installed with them. So if we're talking about like a Daikin FIT and we're installing that electronic expansion valve cased coil, we're going to add a separate transformer inside the furnace that's going to feed power to our new EEV coil. What a lot of guys are not and gals are not understanding is that transformer is going to be polarity sensitive. So with transformers, we really need to ground our common side of our transformer so that we have a path of flow for our current. So anytime we are installing a separate transformer on our communicating system, it is required that we ground it properly. Because what if it's just a zone control panel? You know, if this is a Daikin FIT, it's using an EWC UT3000 zone control. It's the only one that works with the Daikin communicating systems, and it has its own separate transformer that needs to be installed in the furnace. So now if I have a zone control panel on this thing with a cased coil and a furnace, I've got 3 transformers and a power choke inside of that furnace cabinet, all of which have to be grounded, and our polarity has to be correct. So it's going to start with the correct installation of our transformers, just making sure that everything is going to the place that it needs to. If we look at the wiring of that, if we take a look at what's coming from the furnace, we got a 4-wire connector, a cable that is running over to our EEV, and it's going to have the 24-volt power from the furnace transformer landing on C and R, and then we have our 5-volt communicating on 1 and 2. But when we install this cased coil, we install this separate transformer, and right here is the key to it. The separate cable coming up to the EEV coil has a dedicated ground wire that has to be grounded to the same place that that furnace transformer is grounded. And when it gets up here to that EEV, we're going to notice that common from our furnace transformer makes its way through this control board, lands on common of the board, and is grounded. So grounding of this entire network is just absolutely critical. So if we have a system that is not communicating properly, the very first thing that we need to do is we need to verify that we have proper grounds throughout our entire network. So very first thing, verify that we have grounds. So if we've done a physical verification that we've got good ground network through it, how do we test those things? How do we see if it's actually there? Well, if we go back just a little bit to like our diagnostics that we were talking about last week, we actually have some communicating status lights that are on the control boards that will allow us to see how our network is actually talking. So it's a great place to start. We've got typically on our communicating equipment, we have a red communicating LED light and a green communicating LED light. And when we look at those, they'll give us an idea of what's going on, right? So if I've got a single flash on the red light on startup, I've got some kind of a communication failure. If I look over at my green light, it might tell me, you know, if I've got a single steady flash on that green light, that tells me that there's no network found and that I potentially have a broken or disconnected communication. So I have a control wire that is not passing voltage through it properly. So that's pretty easy to find. If I have a solid green light, it's going to let me know that on my data 1 or data 2, something is missing. I've very potentially reversed wires, or I have a short. So it's telling me a little bit more about what's going on this network. So how do we test those? How do we see what they're actually doing? Well, it comes down to understanding that whole DC communicating network, right? If we look at the wiring of a communicating system, and this is for the Daikin, but it's for everybody. If we look at how we're going to wire those, on the Daikin, at the thermostat, we're going to have 1 and 2, that's our communicating DC voltage, and we're going to have 24 volts AC that's feeding the thermostat. So that could be that CTK04, or it could be the new 1+ thermostat, which is a really cool thermostat. They're both talking the same way. That CTK04 was the first thermostat that Daikin used. It was built by Honeywell, and now the new Daikin 1+ is built by Daikin, but they are wired in pretty much the same way. The only difference is the 1+ goes 12CR instead of 12RC. I don't know why they did that. I get a lot of questions about that, but they just did. And then it goes to the indoor unit, and we're going to have 1, 2 for our communicating DC, and then we're going to have that 24-volt AC signal. On the 1+, or on the Daikin FIT, we're going to add that cased coil right on this gas furnace. So we've got our 1, 2 communicating, and then our RC for 24 volts AC. And that's going to control the control board. And then the separate transformer that we installed, that's going to run the electronic expansion valve. You know, it's a lot of current running those windings, so we had a separate transformer. But we notice Go into the outdoor unit. We do not require any more than 2 wires go into the outdoor unit, number 1 and number 2, because our outdoor unit has its own power source, right? It's hooked up to our 230-volt single phase outside. So there is no connection between common or ground between the indoor units and the outdoor units. So we have to make sure that we have a properly grounded outdoor unit, because that ground is going to be the key to make these things successful. So if we look at what's going on that DC signal, why ground is important, I just want to quickly give you a representation of what we are doing in an AC conversion, a rectification to DC communication. In AC, we have this nice clean sine wave, right? If we look at an AC oscilloscope, we're going to see an AC sine wave, nice and clean like that. What happens is when we go through a rectification circuit, we're actually going to start using diodes to kind of block this off on our peaks and our valleys, so that we have a little bit straighter signal. So we're kind of capping it, you know. On AC, we're actually peaking and valleying a lot higher than our reference points. When we say 230 volts, that's an RMS voltage. We actually have higher voltages than that. So what we're going to do here is we're just going to limit. We're going to cap it with our diodes. And then in the middle, we're actually going to add a grounded reference point, okay? It's pretty simple. So now what ends up happening is we have everything above ground is now going to be a positive signal, and everything below ground is going to be a negative signal. And we are going to use that to talk with. So we are going to have number 1 on our communication circuit is that positive signal with reference to ground, and number 2 is a negative signal in reference to ground. They total about 5 volts DC. But there's going to be a difference between them, because remember, if Daikin says on theirs, typically from ground to 1, we're going to have about 2.8 volts DC positive, and from ground to number 2, we're going to have around a 2.2 volts DC in reference to ground. So total voltage, our whole bandwidth is about 5 volts DC, because we were just splitting up a 5 volt DC signal, putting a ground in it, going above, and then going below. Well, if we put our meter on that, we're not going to see 5 volts DC. We have a positive 2.8 and a negative 2.2. That's going to leave us with a difference of 0.6 volts DC. So if I take my meter and I check between number 1 and number 2, I'm actually going to have a 0.6 volts DC bias. The difference, the bias is going to be the difference between those. And that's that bandwidth that we're going to talk on, that difference in between that. That's where all of our signal is going on, is in that little bandwidth in between those voltages. So we have to have a bandwidth to be able to get all of our signals through there, just like we have to have a bandwidth for any type of other communications. So it's important to understand that bias. If we look in the installation manual, it's going to be very specific on that bias. It's going to tell us that we need, on number 1, a positive signal with reference to ground of about 2.8 volts and a negative signal of around 2.2, a bias of about 0.6 volts difference. If we have a long control wire, because we can run 250 feet from our indoor unit to our outdoor unit. If I've got over 100, probably if I've got over 75 feet of control wire, anytime I'm adding length to my control wire, I'm adding load onto that 5 volt DC signal, and it's going to drop our voltages, right? Anytime we have long lengths of wire, we're going to have a voltage drop. So we could potentially lose some of our voltage and get down below 0.6. Or say I add a zone control panel. If I add a zone control panel, I'm adding an additional smart thermostat, communicating thermostat. So I'm adding more load to my network. So I have the potential for my bias to go down below 0.6 volts. Hopefully it doesn't. Hopefully I fire this thing up and I have 0.6 volts bias between those. If I don't, now I have to do something about it. So what they have provided is they have provided a bias balancing, and it's in the outdoor unit. So on the outdoor unit, we have a switch called DS1. And what DS1 will do is it will open up that bias so that we have a better bandwidth to communicate on. So we can simply, if we do not have 0.6 volts, we can go to the outdoor unit, we can turn power off to the outdoor unit, we can flip DS switches over from on to off, and we can power that system back up, and hopefully our 0.6 volts has showed up. A lot of guys and gals will say, hey, why don't we just flip those DS switches on from the beginning? I go, well, it's not there for that. It is a fix for when we need it. So we don't use those bias switches unless we absolutely need them. If we have additional load on our network because of long lines, or we have additional equipment, then we may have to adjust our bias. Because if we walk away from this piece of equipment and we have less than 0.6 volts DC bias between 1 and 2, someone's coming back to work on this thing probably the next time that it rains, because then we're going to have a change in current, change of load, and we're going to affect the load that's on that network. So it's critical to have that 0.6 volts bias between the two. And we can check those too. If we look at the actual individual network, I should be able to take my meter and go between 1 and 2 anywhere in this circuit. I should check it everywhere. If I have a problem with my communicating network, so say maybe one of my pieces of equipment is not showing up, I need to take my meter and I need to check between 1 and 2 at my coil, 1 and 2 at my thermostat, 1 and 2 at my furnace, and 1 and 2 at my outdoor unit to verify that my entire network is talking properly. And we also need to verify what that voltage is. So we need to check from common to 2 to see if we have around 2.2, and common to 1 to see if we have around 2.8, because what we have seen is, say I had at the thermostat 2.8 on number 1 and 2.2 on number 2. That would give me my 0.6 volts. And I had the same thing at my indoor unit, I had the same thing at my coil, but I got to the outdoor unit, and say I got to my outdoor unit and maybe I only had 2.5 and 1.9. Well, that's still 0.6 volts, right? But it's the wrong 6 volts. We've had some type of a voltage drop. So even though we had the same 0.6 bias between our network, if we had a voltage drop, that means we had something wrong on that control wire. We had a mouse that chewed into it. We had a staple that an electrician put into it. We had a piece of wire that was rubbing on ductwork. These things were not crucial when we had 24 volts AC, because we were able to still get our current through that conductor. Well, now that we're using 5 volts DC with a very, very, very low load, all of those things could affect the way our electrons flow through that control wire. So the thing that we are finding the most in the field is that if we have a change in that voltage, we got a bad control wire. So at that point, we are going to pull new control wire from our indoor unit to our outdoor unit. And that's typically where you find your fix. But to be able to test those, we are simply going to use our meter on DC voltage, and we're just going to simply check between 1 and 2, and then we're going to check between common and 1 and common and 2. Here's the thing that we see fairly often as well, because remember, going from that indoor unit to the outdoor unit, we have no common, which means we rely on ground, right? Our outdoor unit has to be properly grounded. And we've had instances where we've had outdoor units that had lugs inside of the disconnect that had rusty screw terminals, because sometimes we'll have that aluminum block that our ground wires connect into, but it'll have a steel set screw. So we've had those steel set screws be rusted to the point where we weren't making proper ground. I've had a technician that had to trace the ground wire all the way back to the electrical panel and had 5 full revolutions on the screw in the terminal plate inside of the electrical panel. I've had a technician that had a ground wire that was not connected in the attic inside of a utility box. So these are things that were not crucial to AC. AC used ground just as an emergency. If we had a fault, that was where our electrons flowed to ground, so we had a safety, right? In DC, it's 100% critical that we have these grounds proper. So if we have a problem with voltages on the outdoor unit, or any unit as far as that goes, we have to make sure that our equipment ground is good as well. So you technicians that are working in older homes that have really poor old wiring, don't be surprised to pull out an existing legacy system and put in a new communicating inverter system and the thing not want to talk properly. And then you have to go trace not only equipment, but electrical ground. I've had technicians have to go in and add grounds, because if a furnace is not properly ground, you can add ground to that. You can go find you a water line, a steel water line coming through. You can find copper water line coming through. You can find a steel, gas line. We can find things to add ground clamps to securely ground our equipment. So be aware that ground is going to be a whole new importance when it comes to communicating equipment. If we look at why it's important to have that clean wire, if we think about what a conductor actually is, if I've got a 18 gauge wire, when we were using 24 volts AC, we had a load on the other side. We were turning on a relay or a contactor or a switch or something, right? We were energizing it. So our electrons were flowing through the center of our conductor. And electrons flow like water, so we flow through our conductor when we have a load. Well, that all changed when we went to 5 volts DC, because now we don't have much of a load. We don't have utilities that we're energizing. We're simply communicating. So what we are finding is that those electrons are taking the path of least resistance, which will be on the surface of the conductor. That's where our least resistance is, right? So if we don't have much of a load, our electrons are going to follow the path of least resistance. So what if I've got a wire nut in this thing? Wire nuts have that potential to get corrosion on the copper. As soon as we remove insulation off from copper, all it takes is a little bit of moisture and oxygen and we can corrode our copper, right? So what we're finding is, if you get onto a job and you've got wire nuts that are not properly insulated, you immediately cut those things off and you trim them back to clean copper, and then you fill those wire nuts full of silicone or dielectric grease to make sure that we get no contamination inside of the copper. If we have a control wire that's had a staple on it at some point, that surface of that copper has been introduced to oxygen and potentially moisture, and it's going to oxidize. So there's a lot of times you're going to have to pull new control wire on these inverter systems to get them to communicate properly, because we can have no oxidation on our copper conductor throughout our path. If we do, it's going to cause some problems. So it's a change of understanding in how we communicate. Used to, we would run through the conductor and energize a load. Now we're going to travel on the exterior of the conductor, and it's just a path for the electrons to flow, and there's not a lot of them. I mean, we're really talking low current on this. So understanding that DC voltage is super critical. When we get into checking components, we're still going to operate on our 5 volt DC signal. We're going to use that to flow through our controls. And now we've got 3-phase motors. The best thing that ever happened to a compressor is we left the vapor pump, we took out the permanent split capacitor motor, and we installed an ECM motor. Best thing that ever happened to a compressor. We will not have compressor winding failures like we used to with permanent split capacitor compressors. It's just not going to happen. Same way with our condenser fan motors and our blower motors. So we went from a motor that had 2 windings, a start winding and a run winding, that had different resistances to them, so they had different diameters of wire, and we burn out the start windings pretty routinely in these things, right? Especially if we have a capacitor that fails on them. Well, with an ECM motor, we don't have that anymore. We have 3 windings that have all identical resistance and fairly thick wire. So we're not going to burn out windings like we used to. So it's super easy to check these things. We can check the voltage tune, make sure that all 3 legs are getting proper voltage. And then we can check to make sure that they have even resistance between them for the condenser fan motor and for our compressor. So we're simply going to check those from winding to winding. And then, like we used to do before on our permanent split capacitor compressors, we're going to check the insulation of our motor. We're going to check mega ohms from ground to the conductor. If we have less than 100 k ohms, we've got bad insulation on those windings. But that's really about the only thing we're ever going to do. We're hardly ever going to burn those things up. So we're just going to check resistance between them. When we're talking about those pressure sensors and those transducers, all we are going to do is send our 5-volt DC signal into that sensor, and it's going to change its output based on a change of resistance, right? It's going to change its resistance depending on the pressure or temperature, if it's a temperature sensor. So literally, all we are doing now is we are taking 5 volts DC, we're going to send in a ground signal with it, we're going to send in 5 volts, and the variable voltage coming back out of that is what is going to run our control board. That's the signal that it needs. So we can check these things either by voltage while it's running, or we can check it by resistance when it's unplugged. So it's very easy to troubleshoot these inverters when we know how they're operating, right? So I can simply take my meters, put it on volts DC, and I can check from from number 3 to number 4 to see what the voltage is going in to make sure I got 5 volts DC. And then I can check from ground to number 1 to see what my voltage is coming out. And then I can look at my chart and it will tell me what it is actually reading. A lot of thermostats, you can even walk over to the thermostat and go into the sensor status menus and look at these readings. You don't even have to put your gauges on them. You can go look at all of these temperature sensors and pressure transducers. I do highly recommend that you have a set of micro leads for your meters so that you can get inside these little plugs, but it's not hard at all. It's taken a lot of the unknowns out. You know, these things are operating off from 5-volt DC inputs. So all we're doing is just measuring what those readings are coming from them. Our electronic expansion valve, it's really this simple. It has 4 windings in it, all referencing back to ground. It's running on 24 volts AC. That's why we're using that separate transformer. If we're going to open an expansion valve, we're just going to fire it 4321, 4321, 4321 until we open it up. When we close it back down, 1234, 1234, 1234. So we can check the resistance on those windings to make sure that they are good. So with our Daikin EEVs, we're simply going to unplug our plug. We're going to put our meter on ohms, and we're going to check between number 6, which is the common point, and check 6 to 4, 6 to 3, 6 to 2, 6 to 1. All of those should be between 40 and 50 ohms. If it's outside of that range, it's bad. It's that simple. It means that it won't allow it to open and close properly. When you fire up one of these units, you're going to hear that EEV opening and closing, and that's all it's doing is it's just firing at those individual windings, trying to open that thing up. Moving some of these expansion valves will run a couple thousand steps in 1/8 of an inch. That's a lot. All it takes is for one of those windings to be out, and that thing is not going to open and close properly. And they're removable. You know, it's a external component. If we have a bad EEV, it's literally unsnap it, unplug it, plug in a new one. So a very simple operation. If we're looking at that, like I said, it's between 40 and 50 ohms. If we're looking at our temperature sensors and pressure transducers, we have a chart in our installation and service manuals that shows us exactly what those should be. The only one on these that are a little bit in a different range is that discharge temperature thermistor, because it's on the discharge pipe. It's pretty hot, so it's got a different range value to it, but it's doing that same thing. If we're checking for DC voltage, it's the exact same way throughout our transducers and throughout our temperature sensors. So if I have on a 95-degree day, if I want to check my temperature sensor, because say maybe I've got a fault code that my outdoor temperature sensor is out of range, or it's open, or it's shorted or something, I can literally go unplug that temperature sensor, put my meter on resistance, and measure the resistance on it. So that thermistor is going to have on a 95-degree day a resistance value of 13 k ohms. If it's a discharge temperature sensor, it's going to be a little bit higher. It's going to be 147 k ohms. That's all. It's literally just measuring resistance across it, and it will be either accurate or bad. That's it. There's no in between. Either it is working or it is not. And so we can check it either unplugged by resistance, or we can check the voltage, because we're going to send 5 volts DC to it, and it's going to change the resistance coming back out. And so we have that value right here that will show us. So we can either check it while it is running by checking the DC voltage coming back out of it, or we can unplug it and we can check the resistance. So becoming a technician working on inverter technology may seem like a daunting task. When it comes down to it, there is a lot more information there than you would ever imagine. It's just understanding how that information works. You know, they even give us physical diagrams to see where every one of these components are, so we don't even have to look for them. If I get an error code on my diagnostics that says that I'm having an issue with my outdoor air thermistor, I can look at my piping chart and go, oh, it should be right there by the condenser coil. Or if I got an error for my liquid pipe thermistor, oh, I better go out there and look close to my service valve, right? If it's on the indoor unit, I got a error code on my indoor unit for a gas pipe thermistor. Well, there it is. It's after, here's my expansion valve, so it's after my expansion valve. It's not the first one, because the first one's the liquid pipe, so it must be the one that's on the outlet of the coil. It's the one that's helping read superheat. So very simple to see the layout of these things. We just have to take time and look at the diagnostics, see what the diagnostics are telling us, and then get our tools, get our meters, and go out and find those components and test those. That's all we're going to do, is just check them. We've got the ability to look at faults. Our particular menus will allow us to look at the last 6 previous faults in that unit. Some systems will go a lot further than that. We can go into the lower layer, the monitoring mode, and look at all of those readings. So every one of those temperature sensors and pressure transducers, I can look them up in the menus and see what they're actually reading. Because if I get a diagnostic code for an outdoor air temperature sensor, I want to go to the outdoor unit, I want to go into my monitor mode and see what it's reading. Because if it's a 95-degree day and it's showing that it's reading 50 degrees, I might have a bad sensor. But I need to go unplug it and check the resistance on it and verify that. So not a difficult thing to do. A lot of these things even have emergency modes. So as a technician, if we're working on this thing and we say maybe we just can't quite figure it out, we know that we got a communication error, we're not able to get this thing up and running, but we know it's in the communication cables, rip them out. The important part is to get the homeowner comfortable, right? Get rid of the control wires. Put the things into emergency cooling. A lot of these units have emergency cooling. They're going to be locked in. With ours, we can lock them in at 30%, 50%, or 70%. All we do is we go to the outdoor unit. We go to that DS2 switch. And we set it to whatever we want it. We go to our furnace and we put it in. We just jump our fan if we want to, just so that the fan runs continuously. And then we're going to go to the EEV coil and flip those dip switches and tell it as well, so that all of them know, hey, let's just run. Let's run at 30% until someone can figure out this control wire. So we have ways to get around that. We have things that we need to know. And also be very aware that on any communicating network, it all comes back to making sure that those systems are properly ground. A lot of our external and aftermarket components like powered humidifiers and powered dehumidifiers have isolated power sources, right? They have their own power. They're not always grounded. So it's important to know that if you tie in a powered accessory to a communicating system, those relays on the Daikin 1 Plus particularly, it's got 2 sets of auxiliary contacts that you can use. Those are not true relays. It's solid state circuitry through transistors and diodes basically. So it's not an actual gate switch. So if I use a external component like a powered humidifier or a powered dehumidifier, and I run it through the contacts in my communicating system, I'm going to have an ungrounded signal trying to mix with my grounded equipment. And I will tell you that almost every time we have seen this in the field, it has broken the communication in our communicating network. So if you're adding a powered accessory to any communicating system, add you an isolation relay, because that takes it out of the circuit. It takes that potential voltage out of there and allows our switch just to be a switch. So troubleshooting and diagnostics with inverters are nowhere near as difficult as we sometimes allow them to be. We just have to understand this. It's communicating typically on our 5-volt DC signal. It's crucial to have ground. It's crucial to have non-interrupted control wires. And it's important to understand how to use your diagnostics to get you to the troubleshooting. Learning how to use your meter on 5-volt DC is going to allow you to become a good technician on inverter technology. So that's really about all that I have for this program. I'm going to make sure I'm going to open up all of the microphones right now. And does anyone have any questions about troubleshooting, communicating inverter systems? All right, well, I appreciate everybody joining us. I'll take this video, I'll break it down into some short videos, and that way if you want to go back and just review any of the individual parts, I'll try to have that done. I'll be working on that today and tomorrow. I'll at least have this video done today, and it'll be back up on YouTube at Johnstone Solutions University. Please check us out, and make sure to to join in, to subscribe to the channel. We're almost to 1,000 subscribers. It's so exciting. We're like 965 or something like that this morning. So thanks for joining us, everybody. Have a fantastic day, and we'll see you all next week.